Hey everybody, and welcome to another physics lesson. In this video, we're going to start rotational motion, where we focus on the idea about objects spinning rather than moving in a straight path. We probably should flash back when we started linear motion. Let's start with linear displacement. When it was first introduced, it was defined as a change in position, which was represented by the variable delta x or delta y, depending on the dimension you were talking about. Linear displacement answers the question, how far is the object from where it started? So, how does a concept transition to rotational motion? Instead of linear displacement, now we're talking about angular displacement, the change in the angle as an object rotates, which will be represented by the variable delta theta. Below, you might see a familiar image known as a unit circle. We'll be referencing the unit circle on describing how much an object rotates. You may have heard the term RPM, which stands for revolutions per minute, which describes how fast an object is spinning. The term revolution specifically defines one complete spin or complete rotation. Using the Earth as an example, it completes one revolution when 24 hours of time has passed. However, we will not be using revolutions as a unit of measurement for angular displacement, but instead, radians will be used. As you may remember from the unit circle, one revolution would equal 2 pi radians. When we talked about velocity, it was defined as the change in the position divided by the time taken to make the displacement. Switching over to rotational motion, angular velocity is the change in the angle divided by the time taken to make the displacement. The symbol for angular velocity is omega, and the equation is angular velocity is equal to delta theta over delta t. Acceleration is defined as a change in velocity over the change in time. With angular acceleration, it is equal to the change in angular velocity divided by the time required to make that change. It is represented by the variable alpha. Omega f and omega I represent the final angular velocity and the initial angular velocity. All these variables have direction. Since an object is rotating, the object only has two directions, counterclockwise, which can be noted with a positive sign or CCW. Clockwise can be marked with negative or CW. An object is capable of moving linearly and rotating at the same time, but what's the connection? If a disk rolls in some direction, there is a relationship between how far the disk travels to the radius of the disk, and is represented by the equations below. Lastly, after displacement, velocity, and acceleration, we were introduced to the kinematic equations, and the same will be done here. You'll notice that the kinematics between linear and rotational are similar. Finally, let's conclude this video with an example. A merry-go-round is traveling initially with an angular velocity of 5 radians per second. A child pushes the merry-go-round over 10 revolutions, causing it to accelerate at a constant rate of 1 radian per second squared. What is the final angular velocity of the merry-go-round? As always, let's start with the known information. The initial angular velocity is 5 radians per second. The angular displacement is 10 revolutions, but it will need to be changed to radians. We can do that by multiplying 2 pi, and it will give us 62.83 radians. The angular acceleration is 1 radian per second squared, and we're trying to find the final angular velocity. Based on the information, it looks like this kinematic would be useful. Final angular velocity squared equal to initial angular velocity squared plus 2 times the angular acceleration times the angular displacement. We can plug everything in, and this will give us an answer of 12.27 radians per second counterclockwise. That concludes this video on rotational motion. Hope you found it helpful, and thank you for watching.